This is the solution for problem 89 from chapter 17. The Catherine wheel is a firework that consists of a coiled tube of powder which is pinned at its center. If the powder burns at a constant rate of 20 grams per second, such that the exhaust gases always exert a force having a constant magnitude of 0.3 newtons directed tangent to the wheel, determine the angular velocity of the wheel when 75% of the mass is burned off. Initially, the wheel is at rest and has a mass of 100 grams and a radius of 75 millimeters. For the calculation, consider the wheel to always be a thin disk. Okay, so for this problem, we're going to do the sum of the moments about point C, which is the center of the Catherine wheel, is equal to the moment of inertia about point C times the angular acceleration. The moment of inertia here is what we have for a thin disk about an axis going through the center of mass. That's 1/2 mr squared. So I can put that in for the moment of inertia here. And for the sum of the moments, we have a 0.3 Newton force at a distance of r from point C. And I get 0.3 for the force times r for the sum of the moments. And so, solving this for the angular acceleration, I have 0.6 over the mass times r. But what we need to realize here is that the mass and r are both functions of time. So now I want to figure out what those functions are. So if my initial mass is 100 grams and the powder is burning at a constant rate of 20 grams per second, I can say the mass as a function of time is 100 grams minus the rate times t. And if the powder is burning at a constant rate of 20 grams per second and I started with a mass of 100 grams, after 5 seconds all the mass should be gone. And if I do 20 times 5, I get 100 minus 100, so that works. Then I can change the grams to kilograms and pull out a 0.1, and I get the equation that I have here. When all the mass has burned away, r is equal to 0. I want to find r as a function of time because I have r in my equation here also. And to do that, I can say the density of the Catherine wheel is constant. The density is the mass divided by the volume. And I can say the mass that I started off with divided by the volume that I started off with. And initially the mass is 100 grams, so that's 0.1 kilograms divided by the volume. The area of the wheel here to begin with is pi r squared, and since this is divided by the volume, I just said that the thickness here is h. So this is the volume of the Catherine wheel. Initially, at any point in time, the volume is the mass at that time, which I get from my function up here, divided by the volume at that time. So here r is a function of t, and that's pi r squared times the thickness h for the volume at some time. Then I solve for this r, which is really a function of t, and I get this equation here. Then I can take this and put it in for r here, take this equation and put it in for m here, and then I get my angular acceleration as a function of time. And simplifying it gives me this. I was asked to find the angular velocity when 75% of the mass is gone. The angular acceleration is the derivative of the angular velocity with respect to time. So if I want the angular velocity, I take my angular acceleration and I integrate with respect to time. Since I'm integrating with respect to time, I need to find my upper limit of integration, which is when 75% of the mass is gone. If I want the time when 75% of the mass is gone, if it takes 5 seconds for 100% of the mass to disappear, then it takes 0.75 of 5 seconds for 75% of the mass to disappear, and that's 3.75. So my upper limit of integration is 3.75. So then I take my angular acceleration, integrate it with respect to time from 0 to 3.75 seconds, and I get the angular velocity when 75% of the mass is gone, which is at 3.75 seconds, is 800 radians per second. And that is problem 89.